So welcome to our last 2 weeks of Organic Chem. The last 2 weeks is going to be an introduction to organic chemistry. It'll allow us to kind of touch on the naming, talk briefly about chemical reactions. This week we're going to start with the simplest types of organic compounds, and we'll go from there. Now, organic compounds, organic chemistry, deals with a specific element, and that element is carbon. Carbon is able to form 4 bonds. If you remember and you think back to bonding stuff, carbon has 4 valence electrons, which allows it to form 4 bonds. That diversity of bonds that carbon can form allows it to form all of these different compounds, from the glucose that plants make in photosynthesis, to the ethanol that is sometimes in beverages, to the chemicals used in explosives and the chemicals that we use to drive our car. So all of these are organic compounds because they contain carbon. Fossil fuels are organic compounds, and that's where we're going to start. We're going to look at hydrocarbons. Hydrocarbons are organic compounds that only contain hydrogen, and they only contain carbon. Those are hydrocarbons. Now, these come from, ultimately the source of energy for these hydrocarbons is the sun, because plants will take the energy from the sun and undergo, and through photosynthesis, that energy will be changed into chemical energy stored in the plant. That plant might die, or it might be eaten by something else, which is eaten by something else, which might die. And over a long period of time, and high pressures and temperatures, those things will become coal, oil, or gas, which we use now as hydrocarbon. And when we burn those things, we release that carbon in the form of carbon dioxide. Now, organic chemistry does not include a couple of things. So it does include things that contain carbon. So here in the organic club, you see glucose, you see ethanoic acid. You could even put in something that, like CCl4, carbon tetrachloride, is an organic compound. It's a carbon-containing covalent compound. There's pentane, there's methane here, CH4. But there are some carbon-containing compounds that are not organic, and it's easier to remember those because the list is a lot smaller. Carbon oxides, so carbon dioxide and carbon monoxide, and ionic compounds that contain carbon, like calcium carbonate, or the cyanide ion is inorganic. It's not organic. Those are things that are not organic compounds, and that list is far shorter than the things that are organic. Now, when we name organic compounds, there are some prefixes that we need to be familiar with. The ones you're probably most familiar with are 5 onwards. Pent, hex, hept, oct, non, and dec are very familiar because those are the same prefixes that we use in mathematics. However, the first 4 prefixes are a little bit unique. So meth is referring to a 1 carbon long chain. Eth is talking about 2 carbons. Prop is 3 carbons, and bute is 4 carbons. You'll notice these endings are ane, so methane, ethane, propane, and butane, etc. Those are talking about the types of bonds. You're going to learn in these 2 weeks that the prefixes and the suffixes, like ane is, gives us a lot of information about the type of chemical that we have. So methane, the meth tells me that it is a 1 carbon chain. The ane tells me that it's all single bonds with hydrogen. Those are the alkanes. So that would be methane. Ethane, eth, tells me it's a 2 carbon chain. And the ane tells me that it's all single bonds. So ethane would look something like that. So we do need to remember these. When we think about kind of some of the boiling points and physical properties, if you think back to Chem 20, things that are only carbon and hydrogen are going to be nonpolar. So there is only London dispersion force, and London dispersion force increases as the size of the molecule increases. So something like decane is a liquid, whereas methane, natural gas, is a gas. And that has to do with the amount of intermolecular forces. So the alkanes are where we're going to start. So I'm going to draw an alkane and we'll name it. So there's a 4-carbon chain, and we'll talk about some of these rules. So the alkanes have only single bonds present. So there are only single bonded hydrogen filling in the rest of the molecule. And there are some rules when we name alkanes. The first rule when naming alkanes, so rule number 1, is identify the longest chain first. So I look at this and I have a 4-carbon chain. That is my longest chain. That is longer than maybe this 3-carbon chain right there. I go with the longest chain first and I name it. So that 4-carbon chain is bute, and because it is all single bonds, that is butane. The next thing that we do is we identify any side chains. So side chains, like this would be an example of a side chain. They're not part of that longest parent chain. When we name side chains, we use the same prefixes. So we look at this side chain, and that side chain is a 1-carbon side chain. That's meth. But because it's a side chain, it's a ol. So that is a methyl. So we put the side chains in front. One thing with the side chains is we do put them alphabetically. So that would be methyl butane. The other thing we need to do is we need to identify which carbon that this methyl is on. So the other rule is when we number these parent chains, we number it so any side chain has the lowest number possible. So I have 2 options. I can number this 1, 2, 3, 4, which is incorrect because that methyl is on the 3rd carbon. It's far better to go 1, 2, 3, 4. So now that is methyl is on the 2nd carbon. So the name of that compound is 2-methyl-butane. Butane is my longest chain, and there is a 1-carbon chain on the 2nd carbon. One other thing you might see, so maybe instead of a carbon there, I have another methyl. We would name that, so it would still be methyl, but because there are 2, we would say dimethyl. So the di tells us that there are 2 methyls there. The numbers still tell us which carbons there are on. And this is kind of redundant because the numbers and the di both tell us that there's 2 methyls. But we do need to know the location. So the name of this compound would be 2,3-dimethylbutane. So 2,3 because on the 2nd and 3rd carbon there are methyl groups, and butane is my parent chain. So that's how we name, drawn in the expanded formula like the previous question, where we see all alkanes. Now, other ways you might see them. So you might see carbon chains or compounds drawn like this, where every single one of these points is a carbon. So I could name this one as well. First, I name my longest parent chain. So here is my longest chain right here. And it is 1, 2, 3, 4, 5 carbons long. My longest chain is pentane. Attached to that carbon chain, I have a 1, 2 carbon long side chain. That's an ethyl. And I have a 1 carbon long side chain. That's a methyl. Now I would write these alphabetically. So E comes before M. So I would say 3-ethyl Now again, it's 3 because I want any of those side chains to have the lowest number possible. So I'm going to number right to left. So it would be 3-ethyl, 2-methyl, pentane. So 3-ethyl, 2-methyl, pentane is the name of that organic compound. Now this is a line structural formula. You might see it like that. You might see bonds, or you might see kind of a simplified version where this first one we have a CH3, CH2, then we have a CH with a C2H5 coming off of it. That's my ethyl. Then we have a CH with a CH3 coming off of that. And then we have a CH3. I guess that'd be a CH4. Right? This is 1, 2, 3. No, only 3. CH3. So we could see it this way as well, where we'd start from the side 1, 2, 3, 4, 5. So the ones not in brackets are my longest chain. In the brackets, so on the third carbon, there's a 2-carbon long side chain. That's an ethyl. On the second carbon, there's a 1-carbon side chain. That's a methyl. That's another way you might see it in kind of a condensed form. Now these are the alkanes, so only single bonds. They have only London dispersion forces, so as they get bigger, their boiling points go up. One thing you might run into is this idea of isomers. So if we look here, we have C6H14, which is hexane, a 1, 2, 3, 4, 5, 6-carbon chain. If you look at all of these structural formulas, they all have 6 carbons. They all have 14 hydrogens. However, their shapes are all different. We call these structural isomers. So they're chemicals with different structures, but the same chemical formula. Now, in order to count the hydrogens, we would need to go and see how many bonds each of these carbons have made. This one has made 1 bond, so there's room for 3 hydrogens there. This one will have 2 hydrogens. This one 1 because it's formed 3 bonds. This one 2, this one 3, and then this one 3. That's where the 14 hydrogen come from. But hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane are all isomers of each other. Now that was relatively quick. As you practice, this will become a lot easier. You might want to go back and re-watch that part of the video, reintroducing the naming and the drawing of the alkanes. All of the rules we're going to look at are going to be building off of those rules. Now next, we're going to talk about something that's unsaturated. So the alkanes are saturated, meaning that they have all single bonds. You might have heard before of unsaturated fats. Unsaturated is talking about the presence of double or triple bonds. So now when something is unsaturated, it's not saturated. To be saturated, it needs all single bonds. When it's unsaturated, there may be there is a double or a triple bond. When we name compounds containing double bonds, these are called alkenes. And instead of ending with ane, we end with ene. The other rules are the same. So my first rule, again, is I find the longest chain. For alkenes and alkynes, which are 3 bonds, it's important that we remember the longest chain has to contain that double bond. The other thing to remember is we number that chain so the double bond has the lowest number possible. So it's the longest chain with the double bond, which would make this longest chain hex ene. Now that double bond can be in different places, so we call this hex 1-ene because that double bond starts at that first carbon. So that's our parent chain is hex 1-ene. The other rule stays the same. So this is an ethyl side chain. It's 2 carbons long. I have a methyl here and a methyl here. So because E comes first, I will start with 4-ethyl. So that's 4-ethyl. And then 4,5 dimethyl hex-1-ene. So 4-ethyl 4,5-dimethyl hex-1-ene is the name of this compound. The hex-1-ene again comes from this 6-carbon chain with a double bond. That makes it ene. Ethyl comes before methyl, so I start with ethyl. On the 4th carbon, I have an ethyl, and on the 4th and 5th carbon, I have methyl groups. That's why it's dimethyl. These are the alkenes. So we know it's an alkene because the ending is ene. Now, alkenes are still nonpolar. They are more reactive because they have this double bond. And so things like chlorine or hydrogen can attack these double bonds and undergo what are called addition reactions. However, their physical properties are pretty similar to the alkanes, where they have only London dispersion forces, and as the molecules get bigger, the boiling point and First, we name the longest chain. We try to give any side chain the lowest number possible, except if there's a double bond, then that gets preference. We name the side chains, we name the longest chain. The numbers tell us where on that parent chain the side chains are. We put those side chains in alphabetical order as much as possible, and then we name it in that way. So that's what makes something organic. That is how we name alkanes, alkenes, and alkynes. And that's where we're going to start this first week. Forces go up. Here's a drawing one. So 2-methyl-but-2-ene. My longest chain is but. So 1, 2, 3, 4 carbons long. That 2-ene tells me that that double bond is on the 2nd carbon. So I would draw it like that with a structural formula. And the 2-methyl tells me that there's a methyl group on that 2nd carbon as well. So this would be 2-methyl-but-2-ene. Just to review, now alkynes has an ending -ine, meaning that there's a triple bond. So maybe 1, 2, 3, 4, 5, 6. Now the thing with triple bonds is because these triple bonds they really lock those atoms in place, is sometimes you might see them appearing very linear, because that's how they actually appear in reality, where this is my 1st carbon, 2nd, 3rd, 4th, and then they start to bend because they can undergo those kind of tetrahedral bond angles. But a triple bond really locks it in space, and it might appear more linear. So this would be hex because it is 6 carbons long. And on the 2nd carbon, there's a triple bond, so it'd be -ine. So ane is all, that's not ane, that's and. So ane is all single bonds, ene is double bonds, and then ine is triple bonds when it comes to naming alkanes, alkenes, and alkynes. One way that we can identify alkenes and alkynes is what's called a bromine test. So bromine is a brownish liquid. When we put it in an alkane, nothing happens. So alkanes, the bromine will still appear brownish when mixed with an alkane, meaning that the thing is saturated. If something is unsaturated, so if it's an alkene or an alkyne, so if it has double or it has triple bonds, then it will undergo an addition reaction, and that bromine will actually go colorless. So that's one way that we can identify whether a compound is saturated or not. So the naming rules,